Hello, everyone, and welcome. My name is K C Lin. Today, we're diving into a fundamental concept in mathematics and computer science, interpolation. Interpolation is the art and science of estimating new data points within the range of a known set of data points. Think of it like connecting the dots. When you have a few scattered points on a graph, interpolation provides a way to draw a smooth, continuous line or curve that passes through all of them. It's a powerful tool used in many fields. For example, meteorologists use it to predict temperatures between weather stations. Computer graphics artists use it to create smooth, realistic animations and shapes. During this presentation, we'll explore different types of interpolation, like linear interpolation, which is the simplest form, and more complex methods like polynomial interpolation. My goal is to help you understand the core principles and see how this is essential to the world around us. So, let's get started. Interpolation is a method of estimation and a field of mathematics that focuses on finding approximate solutions to complex problems. The key idea is that we are working with a discrete set of known data points. These points might represent the values of a function for a limited number of an independent variable. For example, if we're tracking a car's speed, we might only have data points for every 5 seconds. We don't know the exact speed at 2.5 seconds or 7.3 seconds. This is where interpolation comes in. The purpose of interpolation is to estimate the value of a function for an intermediate value of the independent variable. It's about building a bridge between the data points we have, creating a plausible and continuous curve that fits the known information. We can visualize this process as drawing a smooth curve through a series of dots. The more data points we have, and the closer they are together, the more accurate our interpolated curve will be. Now, we're going to start with the simplest and most common form of interpolation, linear interpolation. This is the method most of us instinctively use when we need to estimate a value between two known points. Let's look at the first formula on this slide. It is used to compute the linear interpolant through the two given data points, x0, y0, and x1, y1. Let me break this formula down. The term y1, y0 divided by x1, x0 is the slope of the line connecting the 2 points. What we're doing here is essentially finding the equation of the line that passes through the points and then using the equation to find the corresponding y value for any new x value that lies between z0 and x1. Now, what happens if we have a set of many data points, not just 2? That brings us to the second part of the slide, where we have multiple data points, and here n denotes an integer number which can be much greater than 1. We can perform piecewise linear interpolation. This is where we apply the simple 2-point formula to each pair of consecutive points. The formula for this is shown in equation 2, which is very similar as equation 1, except that we use a subscript index I here. The subscript index I is ranging from 0 to n that is 1. That means we have n-line equations here for the given n plus 1 data points. The index I simply means we apply the formula for the I plus 1 segment of our data.
For example, we would use the equation of I equals 2 to calculate the value y for x between x2 and x3.
Equation 2 can generate piecewise continuous linear interpolants. It passes through all of the given data points.
However, it's important to note that the interpolant is not smooth. At each pair of the jointed points, the slope of this piecewise continuous line changes abruptly.
This means the derivative is discontinuous at these points. This is one of the main limitations of linear interpolation.
And it's why we sometimes need more advanced methods, which we'll discuss later.
However, linear interpolation is incredibly useful in practice because it's computationally simple and easy to understand.
And it provides a good first approximation for filling in gaps in data.
Especially when the underlying relationship is reasonably linear over short intervals. Now, let's look at an example to see how linear interpolation works with a set of data.
As you can see on this slide, we have a table with 7 data points, the index I from 0 to 6. We have the xi and yi values for each of the points. On the right-hand side of the slide, we have a graph that visualizes the data and a series of straight line segments. The graph is formed by the linear interpolants for this set of data, and each segment connects 2 consecutive data points. Let's imagine we need to find a value that isn't in our table. For instance, what is the value of y when x equals 1.5?
First, we need to find which 2 data points our desired x value lies between.
Looking at the table, we can see that x1.5 falls between the data points, y1 1 and x2 2. So we will use the y data of these 2 points, and y1 due to 0.8415, y2 due to 0.9093. Now we can plug these values into our linear interpolation formula. Then we can have y equals 0.87. So the interpolated value for y when x is 1.5 is approximately 0.87. You can eyeball this on the graph, find where x equals 1.5 is on the horizontal axis, and trace up to the line segment between the 2 points. You'll see that the value on the vertical axis is just a little bit above 0.8, which matches our calculation.
Simple example demonstrates the power of linear interpolation. We can use a small set of known data points to estimate a continuous curve and find values at any point in between. While this method is straightforward and effective, it's important to remember that the result is an approximation. The accuracy depends on how closely the actual underlying function resembles a straight line between the points. In our next segment, we'll explore more sophisticated methods that create smoother and more accurate curves. But for now, this is a great foundation to build upon.
All right, everyone, let's settle in and continue our discussion on interpolation. If these linear interpolants are insufficient, what's our next step? The logical move is to find a single, smooth curve that passes through all of our data points. The most common way to do this is by seeking an nth-order polynomial interpolant, such as equation 3. Our goal is to find the specific values for the coefficients from a sub-0 to a sub-n, such that the polynomial go perfectly through every single one of our known data points. Today, we're going to explore 2 primary approaches to determine these unknown coefficients. But a word of caution before we begin. While powerful, high-degree polynomials can sometimes behave unexpectedly, they can produce erratic, wiggly results, especially near the edges of our data set. So it's something to keep in mind as we proceed. The first method we'll examine is what we can call the traditional approach. It's the most direct and perhaps the most intuitive way to solve the problem. Let's say we have a set of 7 data points, as in our example.
A fundamental theorem of algebra tells us that for any set of n plus 1 points,
there is a unique polynomial of degree at most n that passes through all of them. So, for our 7 points, we are looking for a unique 6th-order polynomial, which you see written here. The method is straightforward. We take our general polynomial function and substitute each of our 7 data points into it. Since each point has an x value and a y value, plugging in one point gives us one equation. If we do this for all 7 points, we end up with 7 linear equations, and we have 7 unknown coefficients. It's a classic system of simultaneous equations. After solving that system, which can be quite a bit of work by hand but is straightforward for a computer, we get the specific values for the coefficients from A6 down to A0. The graph you see on the right shows the result, a single, smooth curve that perfectly intersects every one of our data points.
It's a great solution, but as the number of points grows,
Solving that system of equations can become very computationally intensive and potentially unstable.
This brings us to our second method, the Lagrange approach.
This approach is much more elegant to arrive at the same polynomial without having to solve the system of equations.
Instead of finding the coefficients directly, the Lagrange method constructs the final interpolating polynomial by combining a set of simpler basis functions.
Look at the formulas, equation 4 here. The Lagrange polynomial, L of x, is a weighted sum of these basis functions, which we denote as et sub I of x. The weights are simply the y values of our data points. The real magic is in how these basis functions are defined.
Each basis function is specifically designed so that it equals exactly 1 when x is at its corresponding data point, x sub I.
And it equals exactly 0 at all other data points, x sub j.
Think about what this means. When we calculate our final polynomial L of x at one of our data points, say x equals xk, every single term in that summation becomes 0, except for the one term where the basis function is L sub k of x. Therefore, L of xk equal yk, where k equals 0, 1, etc., as shown.